Good morning to you. Hello, good morning. So let's start the session. Can you hear me?
Yes, sir.
Hello, can you hear me?
Yes, sir.
Right. So the last week we have discussed some factorial designs. So I suppose that you are familiar with these designs now. Let's move to the other part. It's called orthogonal designs today. So we have discussed experimental designs and what are the advantages of such using such design and statistical designs, and what are the factorial designs. So we have discussed two factor methods, three factor methods, and also finally mixed factor factorial method. So I suppose that you all can design now, apply those factorial designs in your research and product developments. So today I will discuss with you some new and some other methods as well. So we are moving to the orthogonal design. So this is a little bit new word, orthogonal design. So it is actually a statistical word. So you may heard that one before this lecture. So suppose some in your statistic lectures as well. So orthogonal designs means totally different, as we the totally different thing with the factorial designs. And here you can see a graphical abstract related to the orthogonal design. So there is a researcher has developed this antioxidant, this tablet, using different antioxidants. Here you can see 5 antioxidants. So in designing this medicine, it is important to use the proper design. So that's why he or she has used this orthogonal design. This is the cell line. It means the researcher he or she has done some experiment with this cell line. Cell line means when we are doing some practicals, it is important to measure whether it is okay for us humans, or sometimes we can do trials with rats or rabbits, like animals. We call it as animal testing, and after conducting animal testing we can move to the human trials. So you can remember with a very good example with COVID vaccine. You all are familiar with that example, right? Then this is the cell culture, and here you can see the design. The researcher has used what are the how many designs we can use, right? Here you can see 5 ingredients, and finally the researcher has used only 5 experiments. Out of these 5 experiments, after conducting these 5, the researcher has selected the effective one, right? Then design this, right? This is one example. So we have used similar examples for factorial designs as well. But in the orthogonal design, we can reduce the number of trials. We can further reduce, right? And when it comes to orthogonality means there are so many definitions with the industry. So if it is a industry, software industry, the definitions, there are some unique definitions, but when we summarize it, it is actually what is the effect. If there are 2 vectors, we can multiply the corresponding elements together and get the sum of these elements. Finally, it should be 0. Right here you can see for A, there are 4 numbers. For B, there are 4 numbers again. Then what we are going to do is multiply this vector by this one. 2 multiplied by minus 4 plus 3 multiplied by 1 and plus 5 1. Likewise, finally, the sum of these multiplications should be 0. It means the independence, right? Orthogonality means it always show an independence, and also there are effects and interactions as we discussed in the previous discussion. So I will explain this further. Here you can see again the balance and unbalance experiments. Here you can see all the subtypes are similar, but in this example, the middle one is different. So we call it as unbalanced one. And when it comes to software engineering, we also use orthogonal design. Here you also can see the effects are not there. It means independent. So here there are 2 axes, x and y. So what happened when we change the x while maintaining the y as constant? It means we are not changing the y, but we are changing x. So you can get this type of graphs, right? So it means those are orthogonal. So, but we can't change 2 factors together here. If it is orthogonal design, so we are not going to change 2 factors. 1 factor should be maintained as constant. Then we are going to change other factor. If not, finally it means there is no correlation, right? It means the test is independent, right? Right? That is summary. Okay. And in this design, right? In this design, you can see 3 factor method here. There are 3 factors at 2 levels, right? So these are the 3 factors, 3 columns. And if it is, as we have discussed, if it is orthogonal design, the multiplication, the sum of multiplication should be 0. So here we can see in this example, we can see we are going to multiply A and B. Then what happened? The result is 0. Then A and C, result is 0. Then B and C, again the result is 0. So it means this design is orthogonal, right? How many factors are there? There are 3 factors. How many levels? We are going to check 2 levels, and the sum of multiplications are again 0. So it means this design is an orthogonal design, right? A is independent design. A එක independent because ඒකත් එක්ක මේ වගේ interactions තිබුණට there are interactions, but there are no correlations නේ. ඒත් එක්ක මේවා depend වෙන්නේ නැහැ, right? So it means it is orthogonal. Orthogonality guarantees that the effect of one factor interactions can be estimated separately from the effect of other factor, right? So can you remember the style that we are writing designs in factorial designs? I think you are familiar with, but in orthogonal designs, the style is different. You can remember we wrote 3 factor method and 2 factor method. There is a unique one, but here a different one. Here we use different terms. Runs means a number of rows. We will discuss. So I will discuss this example. So here you can see again the very simple example, preparation of cup of tea using 3 ingredients, sugar, tea, and milk. Therefore, number of factors are 3. So it's clear, you all know, sugar, tea, and milk, 3 ingredients. That means there are 3 factors. And we are going to check at 2 levels. 2 level. So always you can remember when we are using plus minus 0, 1, 2, 0, 5, 10, but we have to justify it. We are going to use this -1 as a low level and +1 as a high level. So how many levels are there? When it comes to conventional test method, there are 3 factors at 2 levels. So 6 test cases should be there. Ne? Factorial design cases higher. But here you can see only 4 cases. Right? How to get these things, I will explain, right? Right? It's actually L4 design. Here you can see 4. Right? 4 means number of rows. As I explained here, number of runs mean number of rows. Sorry, number of columns, right? Levels means levels. Here the levels. And runs means number of rows. So number of rows and number of columns are important. Here you can see 3 columns, and 4 rows, and we are going to check at 2 levels. So therefore you can see 2, right? So this is the orthogonal design. You can see 4 test cases should be conducted, but we use the same example for conventional method. It means factorial designs. So you can see we have to do at least 6 trials. That is the difference in orthogonal designs, right? And if we are using here, you can see a comparison, conventional methods and orthogonal test methods. Conventional means we have already discussed factorial designs. If there are 3 factors at 3 levels, so we have to do 27 trials. But in orthogonal test cases, if there are 3 variables and 3 levels, we have to do only 9 trials. That is the difference, right? There are some examples you can read. And here also a very good example. 3 parameters at 3 levels. There are 27 cases should be conducted when we are using conventional method. But you can see in orthogonal array system only 9 trials. So how to write these 9 trials? It is actually a statistical method. So you can use Minitab to get these designs. I will show you how to do this experiment by using Minitab later. And this is the method, right? In this example also you can see conventional method. There are 3 factors at 3 levels. These are the 27 designs. Right? There are 3 factors at 3 levels. Here he has used different colors for levels. So as we have discussed, we can use minus, plus case and 5, 10 case in any case. In this example, the researcher has used colors, different colors for different levels. So here you can see how to use 27, how to do 27 trials. But as we have discussed, in orthogonal designs, only 9 trials are there. How to get this design? Right? මේ සාමාන්‍ය conventional method එකේ 27ක් කියනවා, මෙතන එන්නේ 9යි. එතකොට මම ඔයගොල්ලන්ට කියලා දුන්නා මේක statistical design එකක්. And here you can see the relationship, right? Second. එතකොට මේ conventional method එකේ second එක තමයි මෙතනට එහෙමම ඇවිල්ලා තියෙන්නේ. Fourth. Similar නේ? Fourth, red, green, red. Red, green, red. And ninth one. Again, you can see ninth one, red, blue, and blue. Red, blue, blue. Likewise, there are some similarities. Similar cases are there. And numbers 2, 4, 9, 12, 14, 16, 19, 25, and 26. These are the selected cases. Right? This is actually a statistical design. So it is very difficult to determine these orthogonal designs. So What we have to do is there are statistical software. So if we have to select only number of factors and cases, then we can get the design. Questions, Tinada Munahari? Do you have any questions?
Sir,
Oh,
can you explain example 1 again, sir?
this one.
No, sir.
Which one? Previous, this one? This one?
Yes, sir.
This one?
Oh,
Right. Here, this is very first example. Here we have used 3 factors. It's clear, right? Sugar, milk, and tea. How many levels? 2 levels. Right? So if we are going to conduct a conventional method, so 2 multiplied by 3, there are 6 cases have to be conducted.
yes, sir.
Right. But in orthogonal array system, there are only 4 cases. I will explain how to get this system, right? How many factors are there? 3 factors. How many levels? 2 levels. So we have to select 4 factor method. So ඔයාලට තියෙන ප්‍රශ්නේ මොකද්ද? කොහොමද 4 factor එක ගත්තේ කියලාද?
Oh, sir.
So that is standard. ඒක standard එක statistically design කරලා තියෙනවා. දැන් ඔයා Minitab එකට ගියොත් orthogonal designs වල there are so many designs. So based on our number of factors and levels, it means based on our experiment, we have to select the design. You need not to remember the design. මේක මතක තියාගන්න අවශ්‍ය නැහැ. මේක ගන්න පුළුවන්. මම හිතන් තේරුණා. අපි ඊළඟට example එක වාට තේරෙයි හොඳට බලමු. Right. This is the table, right? This is the table. So you can select what is the design you have to use. Number of factors, number of levels. If there are 2 factors and 2 levels, so we have to use L4 design. Then you just search L4 orthogonal design and you can download it from the internet, or if not, you can get your own one by using Minitab. I will explain how to do it. That is the method. If there are 9 cases, if there are 9 factors, 9 raw materials, and when we are going to check it at 2 levels, so the design name is L2L design. Right? There another table again. And one example here, L9 orthogonal design. If it is L9, you know 2 or 3 factors. Ne? Here, sorry, 4 factors, right? Any factor you can use. So, method levels 1, 2, and 3. It means 3 levels. 4 factors. 4 factors, 3 levels. So we have to use L9. Right? These are the factors or raw materials, and 1, 2, and 3. These are the design. So levels. So how to mix ingredients together? There are 9 experiments, right? It's clear, ne? It's easy. Then what are the advantages? So you know what is the major advantage? Number of trials have been reduced. Ne? Reduce the number of test cases for trials. Create few test cases which cover all the testing, and complex combination of the variable can be studied. Interactions are there, right? And high productivity and very low. Raw material wastage is very low. Energy wastage is very low, and interactions are there. Those are the advantages. Ne? Where we are going to apply these things? As I discussed with you in the previous one, so those days we use this type of statistical designs in aircraft and automobiles and software designs and programming, like engineering designs we have used. But nowadays we are talking about how to use these statistical designs for food processing, right? So these are very highly recognized, highly applied designs. So it is very important to know how to use these designs. Right? In your life also, we can use you can use these designs, right? They are essential in statistics and they used in computer science and cryptography. Cryptography means data science and what do you call is in software designing, programming, right? Orthogonal arrays are used in automobile design, development of vehicles. They are immensely important in all areas of human investigations. For example, in medicine development, agriculture and manufacturing engineering also we are being used. Orthogonal arrays are related to combinatorics, finite fields, geometry and error correcting codes. So code writing and geography and some mathematics we are being used orthogonal designs, right? So there is no more no worries to consider its reliability. So it's already been tested and applied. Here again we are discussing advantages, so you can read and understand. And Taguchi is one, right? This is a very good design. In your research and product development, we always use Taguchi's design, right? Taguchi is the founder. He's from Japan. He has found this method, statistical method, in Second World War time. For what he has used these methods in communication system development. You know, after Second World War, it is actually very bad time for Japan as well. So all systems of breakdown were not working. So the researchers have developed communication systems among the nation and some telecommunication programs. For these programs, the Taguchi, one of the very famous researcher, he has found these Taguchi's design. It is actually a orthogonal array, but there are some orthogonal designs. So all Taguchi's designs are not orthogonal, right? Based on mixed level, highly fractional factorial designs and other orthogonal designs, there are 20 arrays. Among them, 18 are orthogonal, 2 are non-orthogonal. So we have, can you remember how many designs we have discussed? Normal designs and factorial designs, statistical designs, and orthogonal designs. But now we are at Taguchi's design. Arrays means designs. He has introduced 20 arrays to the world, and among these 20, 18 are orthogonal and other 2 are non-orthogonal. You know what is the meaning of orthogonality? What is the meaning of orthogonal designs? It means independence. Interactions are there, but each factor, there is a independence, right? So you know that is a summary of the things we have discussed today. So now we are moving to talk about Taguchi's design. Basically, we use all Taguchi's designs in the food processing. In your senior students also used, they have used Taguchi's design for their experiment. You also have to use this design in your research, and when you go to the factories and any company, so you can use. Okay. It's a robust design. Robust, you know what is the meaning of robust? We have reduced the noise factors. We can make it errors kuda kadui, right? If it is a Taguchi's design, it is actually a robust design. It means reduce noise. It means a very good design, right? We have reduced errors. And control factors and noise factors are there. It's easy, you can easily understand what are the difference between control factors and noise factors. The control example for control factor is temperature and time, like easily control factors, and we call it as processing parameters. Right? Temperature easily controlled. moisture level like factors you can easily control. But when it comes to noise factors, it is difficult, expensive. It means the humidity, light condition, yogi factors, noise factors. Ne? So we can easily control factors. It is difficult or expensive to control noise factors. As an example, the temperature in your house, in your room. In your room, little bit easy. You have to use a fan or small air condition. When it comes to your house, entire home, then highly expensive. A biscuit manufacturer is needed to optimize the flavor of his product. So the manufacturer has to determine control factors that reduce the effect of noise factors on biscuit flavor. So what are the control factors and noise factors? To the flavor, control factors are example, temperature, time, and moisture, and ingredient level like these things. Noise factors are the room temperature, the environmental temperature, carbon dioxide level, gas mix level. It means percentage, in our air, normal atmosphere, how much the oxygen carbon dioxide ratio. It is very difficult to maintain. Like these factors are noise factors. And there are 3 stages in using Taguchi's design. Yeah. The system design, parameter design, and tolerance design. Right? These are the 3 stages. So we can't use Taguchi's design directly, but we have to consider each level, each stages in design. Right? What is the meaning of system design? It is actually a conceptual design. Right? Conceptual design. The design at the conceptual level involving creativity and innovation. System design is application of scientific, engineering, and technical knowledge to produce basic functional prototype design. This requires a fundamental understanding of the needs of a customer and production environment. Right? It means so you are going to develop a new machine to for string hopper making. Right? You know the demand, customer requirement, and the price, all these factors then small design you are going to develop. Right? You take some aluminum sheets and develop this design. It's a very basic design. Right? Then we are moving to the parameter design. It means robustification is very important. It means reduce the number of noise factors. Sorry, reduce the number of variables. It means in as an example, first design system design RPM it is very difficult to control. But in parameter designs, you have to maintain the RPM at highly standard or correct level. Once the concept is established, right? First, you have to establish the concept. The nominal value of the various dimension and design parameters need to be set. Right? All parameters are now okay. This is sometimes called as robustification. It means reduce the errors. The aim of robustification is to make product or process less variables in the face of variation over which we have little or no control. Right? All these factors are now fixed. Right? RPM is fixed. The dimensions and the speed and the voltage and the feeding rate, all these factors are now fixed. Right? We call it as parameter design. Then finally, the tolerance design. Right? We have 3 stages: system, parameter, and tolerance. System means the conceptual design. We just have to use some raw materials and develop. Right? It is a prototype design. Parameter design also a prototype design. Here it is actually robust design. So very low, no variations. And finally, the tolerance design will successfully complete the parameter design and the understanding of the effect that the various parameters have on performance. Resources can be focused on reducing and controlling variation in the critical few dimensions. These sections deal with the problem of how and when to specify time tolerance for a product or a process so that quality and performance, productivity are enhanced. Every product or process has perhaps a large number of components, right? It means everything we know, what type of resources we need and what are the quality control parameters. We have discussed some of these factors at the first discussion, right? I suppose you can remember. So it means system is basic one, parameter is the middle one, tolerance design is the actual one. So there is no more design. Here also you can see clearly there are three stages. System design is the suitable working levels of the design factors, and under the parameter design, select the proper orthogonal array, how many factors, how many levels, and run the experiment and get the design. It means, as we have discussed, we can use Minitab like softwares and input how many factors and levels, then you can get the design. Then use this design and run and analyze the data, identify the optimum conditions and confirm. It means sometimes you have to use Taguchi's L4 design. There are three factors at two levels. Then how many trials are there? Can you remember? There are 4 trials, and after conducting the 4 trials, you can select the optimum one. Then confirm. We have used Taguchi's L4 design and select the third run. And according to the third run, these are the raw material or condition levels. We confirm it, right? Then tolerance design, determine the result of parameter designed by tightening the tolerance, and we are going to further reduce the tolerance level, right? So suppose you get the thing I just wanted, right? And this is again one example, factors levels, and how many design for factorial designs and Taguchi's design. If there are 4 factors and we are going to check it at 2 levels, so 2 by 4, 16 experiments have to be conducted under the factorial design. But here 4 by 2, only 8 designs. Right? 4 by 2. In this table you can get 4 by 2, right? 4 by 2. Here 4 factors, 2 levels, L8 design. This is the result. Likewise, there are different experimental designs, right? So reduce time, cost, and sample size, effective methods, interactions can be observed. Right. Then how to use the Taguchi's method? There are 4 major steps. First, we have to brainstorm. Right? Brainstorm means what is the design we are going to use? How many factors? How many levels we are going to check? Right? So brainstorming means when we can discuss together, we can discuss as a team. That is called brainstorming. Right? Brainstorming, we can select the design, right? Then designing means conducting experiments and get the optimum one result. So we selected. So we know there are 4 factors and we are going to check 2 levels. So brainstorming, we select. We have to do Taguchi's L8 design. Then design is there. Then we are going to do the 8 trials, conducting experiment. We are going to perform the all experiment and select the best one by analyzing the results. By analyzing the results, you can select the optimum one, and we are going to confirm it. Right? This is the temperature. This is the sugar level. Right? For this experiment, likewise, we can confirm it. So these are the 4 steps. So you have to understand 4 steps. It is very essential. You need to have a good understanding on these steps. And comparison again, Taguchi's design and factorial design. You can see in the slide, basically we use in factorial design number of levels and number of factors. And here, number of rows here, number of levels here, and number of columns here. Design right? Number of rows means number of experiment, number of levels and number of columns means number of factors, right? This is Taguchi's L8 L4 design. So there are 4 trials, 2 levels, 3 factors. It means 3 columns, 4 rows, and we are going to check at 2 levels. Another layer design again. We can write it as L4 within brackets 2 to the power 3 or OA4 2 to the power 3. OA means orthogonal array, right? So make a dekak. What L4 2 by 3 2 to the power 3 ke liya nat puluwan. O OA4 2 to the power 3 ke liya nat puluwan. The difference is here we use L, here we use OA. These are the standard figures, right? Standard methods. So if you have a question in your question paper, select the Taguchi's method or orthogonal design. So you have to write it as mentioned here, and we have to write how many factors here, how many levels so here. So therefore, we are going to use Taguchi's L4 design. Here make a yando. Copy right? So if you then you don't have marks. This is the L4 design. This is the L12 design, right? L12 design, and L16 design is also there. There are so many designs, right? Right? These are the designs. You can download these things. Right? Understood? Again, there is a comparison. If it is a Taguchi's L4 design, you know how many factors, how many levels, how many number of experiment, like these things you can get the information, right? If it is a full factorial design, how many experiment? So Taguchi's experiment design is attack. If there are 7 factors at 2 levels, for Taguchi's only 8. But if when we use factorial designs, then again we have to do 128 experiments. So it's a big one. And here also you can see if there are 15 factors at 2 levels, only 16 trials for Taguchi's design and orthogonal arrays, but 32,000, somewhat around 32,000 for factorial design, which is impossible. It is impossible to do. So that is the importance of using Taguchi's and orthogonal designs, right? In this table, you have to understand why is it important, right? Again, you can see some tables for parameters and levels. Can understand, right? Example, a researcher has been identified sugar, lime, and water as the main ingredient to develop a homemade soft drink. However, he has to add 5% and 0.25 citric acid in order to boost the flavor. Propose the most appropriate experimental design. So how many factors are there? 1, 2, and 3. 3 factors, and how many levels? At what levels? Give me answer. How many factors are there? No answer. Dilrukshi? Dilrukshi, can you hear me?
Yes.
Huh?
Sir.
How many factors?
Three factor.
How many factors in this? Right, 3 factors.
Three factors.
Okay. Then Nadun? Levels? How many levels? We are going to check. Yes, 2 levels. So give me the proper design. How many factors? 3 factors. How many levels? 2. So what is the design? Yes. That is not only L4, that is Taguchi's orthogonal array L4 design, right? Then we are going to use Taguchi's L4 design and explain why did you select the method. There are 3 factors at 2 levels, but there are 2 more ingredients, but we maintain these ingredients as constant for all experiments. So therefore, we are not going to consider these 2 ingredients are factors, right? That is the way you have to write. Okay. Then the last one for orthogonal array related to Taguchi's method. Taguchi has introduced a quality loss function. Right? This is the here you can see traditional quality loss function and also the Taguchi's one. When it comes to the traditional model, you can see lower specification level and upper specification level. This is the target, right? One example here. So you know ice cream, 1 liter ice cream are there in the market. So the company, they have introduced their target as 1,000 liter, sorry, 1,000 milliliters or 1 liter, and lower specification level sometimes around 950 milliliters. Upper specification is 1,050, and the middle value we consider as a target, right? Understood? Okay. Then in the Taguchi has introduced this one, right? So within the target, you know, in the traditional method, there is no losses. Right? But here, the quality loss is 0 only if we are on target. The මෙතන අපි quality loss එක කියලා සලකන්නේ එක්ක මෙතනින් පහළට යනවා එක්ක මෙතනින් එහාට යන්න ඕන. But in Taguchi's method, you can see he has introduced this method. Here the lower specification level and upper specification level, all these things are similar. And he, according to Taguchi, he think, according to the method, this is the only place no quality loss. But there are some quality losses from here to here. You can see. Here to here also you can see. But in this traditional method, we consider it as a quality loss 1 before LSL and after LSL, USL. Right? Traditional, here no losses. But in Taguchi's one, From here to here also we have a loss, but this is the optimum one. It means when we use Taguchi's method, it is actually a robust design. It is the very good design, right? Here also you can see this example. In this picture, you can see lower specification level is here, upper specification level is here. So in traditional method, we consider these three oranges are good. But it's in Taguchi's level, this is the most optimum one, 5th day one. We are not going to consider other 4 orange. It means the correction, the errors are very low. But in traditional method, you can see the. Okay, that's all about Taguchi's design and orthogonal design and all other factorial design. Can you remember the designs we have discussed? First day. Give me an example. Answers දුන්නොත් අපිට ටිකක් discuss කරන්න පුළුවන් නැත්නම් I will move to the other one. It means you can understand, no need to summarize. So you can understand, you can read and understand. So today we have discussed orthogonal designs and Taguchi's design. So you know the advantages, and we have discussed some examples. Please practice, please do some examples as your homework. So suppose there are no more questions. If you have questions, it's your time to ask. And quality loss function also discussed. So then we are moving to the other one. It's about second part of the color. Color measurement we have discussed first part last week. And last discussion. Now we are moving to the second part. ප්‍රශ්න තියෙනවද මොන හරි? No questions, so we can continue. In the color part, last week we have discussed what is color, right? And how to measure it. What are the classification? 3 classifications we discussed, and 8 parameters we also discussed. Hue, value, and you are familiar with how to write colors, how to quantify colors. You are familiar with all these things, right? So today we are going to discuss some color spaces, right? Color spaces, I think Dr. Pulasti also discussed these things, so I am not going to discuss in detail what are the color spaces. And you are familiar with some RGB colors, CMYK, you may heard these colors, spaces. In your printers, and when you go to you have to print a banner or any card from the printing shop, they will ask the design, right? So design, is it okay for RGB and CMYK? They will ask. So in computers and in computers, we basically use RGB color space, but in offset printing, we are using CMYK, right? 4 colors, here 3 colors. So what happened when we print a design directly from the offset print, the colors will fade, because here we use 3 color spaces, 3 color one, but in offset printing they use 4 color. So that is that's why we have to consider the color space, right? Color space එක අනුව printing quality එකත් වෙනස් වෙනවා. But today I'm going to discuss about color measurement or about the printing. So there are 9 color spaces. So many color spaces are available. We are going to discuss with some very important color spaces, right? Here you can see the RGB color space. If it is a red color, pure red means red is there, but no green and blue. Right, here you can see red, then R is there, G no 0, B also 0. If it is a pure green, then green means 0, 1, 0. So green, blue, 0, 0, 1, right? You can understand. And there are some intermediate colors, right? And in RGB color space, in Photoshop, you can see, right? Photoshop 0 to 255. If it is a red, pure red, you can see 255. දැන් මෙතන RGB color space එකේදී මේක තමයි theory එක. In when you use RGB color space in Photoshop like software, එතකොට බිඳුව ඉඳන් 255 වෙනකන් තියෙනවා. It means if we are using 0 to 255 for red, you can see for red 255. Oh, blue means again 255, green also 255. If it is a white color, it means a combination of green, blue and red. Here you can see. If it is black color, black means no colors in order to the RGB. So 0 is value is 0. Okay? You can understand. So these are very simple things. When it comes to CMYK, there are 4 colors. C means cyan, M means magenta, Y means yellow, K means is it K? Sorry. K is black, right? Yes, K is black. In the middle color you can see. But in RGB, RGB colors the middle values, the middle color is white. But in CMYK, you can see the middle color is black, so totally different. And you can compare this in this RGB. When we collect all these colors together, red, green and blue, then total is 255 multiplied by 3, and it is white. But here, what happened when we collectively use all these colors, the middle color is black, and the value also you can determine 255 multiplied by 3. And 0 means white here. So RGB, CMYK totally different. Right? Values, all these things are similar, but color space is totally different. Right? Then compare. HSC color space is there, so you can read and understand. No need to explain further. Right? Here we use hue, saturation, and value. We are not using colors, right? You know hue, what is the meaning of hue, and saturation levels also you know, value is you know. We are not using red, green, blue or CMYK. HSL means again we are going to use the same colors. How to use HSL, right? So you can read and understand. And YUV color space, there are different color spaces. And the CIE is very important. Okay. In some equipments such as colorimeters, spectrophotometers, we are using CIE color space. CI means International Commission of Illumination, right? There are 3 color spaces under CIE. So CIE can introduce colors, 3 color spaces, right? Up to now we have discussed 5 color spaces, and there are 3 color spaces to discuss: CIE LAB, CIE XYZ, and CIE LCH. There are 3 color spaces. So LAB means, L means lightness, A means red green value, B means yellow blue value. And in this example you can see L means lightness, so L0 means it's dark one. Lightness value it's close to white color. If L equals 0, so it is white color. A means red green value, so if it is plus A, it means somewhat around about red color. it is minus A, it's close to green. Likewise, yellow blue, it is minus blue means, sorry, minus B means blue, plus B means yellow. So all these things, L, A, and B are plus value, it means it is yellow, red, it's close to yellow and red, and more lighter product. Okay? L minus means it's close to black. Right? We will discuss some examples. Here you can see some examples and calculations. How to calculate LAB values. So delta L, you know, it's when we are comparing two samples, it is actually there should be two examples. Delta L means L sample minus L standard. If it is a +1 more lighter, -1 darker, we have discussed. Delta A again sample minus standard. Delta B again sample minus standard. We can calculate total color difference, delta E. How to calculate delta E? Delta L square plus delta A square plus delta B square root of the sum. Calculate, right? L2 minus L1 square plus A2 minus A2. A1 square, sorry, square, and B2 minus B1 square, and a square root. You know how to write colors, but today you learn how to calculate the difference in between two colors. Right? Two roses are there, right? L, A, and B. Right. Here, like L is 52. It means somewhat around. It's actually a plus value. It means more lighter one. A 8. A 8 කියන්නේ මේක එක මේ පැත්තට red පැත්තට ටිකක් බරයි but not red නේ. B 54. ඒ කියන්නේ B පැත්තට ගොඩක් බරයි, right? B means yellow. Here you can see නේ. The flower B L29. Whether 52 meter lightness adu, you can understand. A52 means close to red. This is actually red. B22 close to yellow. You can see the yellow also, right? So how to calculate? These are the examples. So again you can see two roses almost similar, but you can see the color LAB values, right? Here 54, here 64. It means this is more lighter. Eh? A8, here A2, here B54, B49. B49 means B reduced means yellow color has been reduced. Eh? Then how to calculate delta E? You know the equation. Delta L plus delta A plus delta B square root. So delta L means L2 minus L1. 64 minus 52 plus 11. Delta A 2 minus 8 means minus 6. Delta B means 49 minus 54, again minus value. So the final answer is 13.70. I think it's easy to understand. Eh? No need to explain further how to calculate the total color difference. Right?
Excuse me, sir.
Yes. Oh, Kian, what is it?
Sir, would you please explain a little bit about that?
How to do this calculation then?
Yes, sir.
Right. Can you understood the LAB?
No, sir.
LAB. Right. You know colors and how to measure it. Here LAB. What is LAB? International Commission of Illumination. They have introduced the three color spaces. The first one is delta. LAB, CIE LAB. L means lightness. L can lightness එක. ඒතර L0 වුණොත් lightness එක 0යි. ඒ කියන්නේ dark. දැන් ගෙදර light නැහැ කියන කරුවලයිනේ. ඒ කියන්නේ 0, right? Dark. L100 වුණොත් it's going to close to white නේ. Highlight. A means red green. එතකොට A minus කියන්නේ green, A plus කියන්නේ red, right? Then what happened when it sometimes, let's say it's plus 54, it is close to red. Minus 20, close to green. Likewise, yellow, blue. Minus means blue, plus means yellow. Right? So it is a plus value, close to yellow. So minus value, close to blue. From 0 to 100, 0 to 100, right? And delta E means the total color difference. It means if there are two colors, two pictures, two food samples, then we can calculate its color difference. You can measure the color here using LAB, and you can measure the color this one and take the difference, right? And you should have and you have to write and you have to comment on the colors by using these LAB values. As we have discussed, if L is a plus value, it's around 52. You know, 0 means black, plus means white. So 52 means somewhat around almost half. So it means it is close to white. It is actually a lighter one, around half lighter one. So A කියන්නේ අපි කතා කරා which color කියලා. So you can comment by using these values. And in this example, I need to calculate delta E. Delta E means total color difference. So delta, how to get the difference of each sample? You know, L2 minus L1, A2 minus A1, B2 minus B1. Right? Here these three values are there. Then delta E means make a වර්ගය අරගන්න, මේකෙත් වර්ගය අරගෙන, මේකෙත් වර්ගය අරගෙන, ඒ වගේ එකතුවේ වර්ගමූලය ගන්න. Then you can get the delta E value. Now it's okay. Malinder?
Yes, sir.
Right. Okay, good. So you can do this example. Please do it yourself. For cinnamon, you can see the LAB values and calculate the delta E value. Right. Easy. This is about LCH. Here again you can see L defined lightness, C is chroma, H means hue angle, right? Then how to calculate the C value? A2 plus B2, its square root. How to get the hue angle? Arctan B divided by A, right? Arctan B divided by A. B means the second sample, A means the first sample. Right? These are the second one, LCH. So this example you can see LCH values, L43, C49 and H60. Here the values are again there. Then how to get the delta L? Delta L sample minus L standard. Sample again standard අඩු කරලා ගන්න. මේකදී අපි මේක standard sample එක මේක standard 47 න් 49 අඩු කරාම ධන 4යි. Right? Likewise, C, how to get the delta C? C sample minus C standard. Right? Always we compare the samples, benchmarking the sample, standard one. Right? So we can get the LCH value. And delta E value also how to get. And here you can calculate C and H. So you need you can understand, right? This is the example. Here we are going to calculate C and H. L, A, B values are there. And you know how to calculate C and how to calculate H, right? C, A2 can make a 46 it's a delta C, right? Please try and explain, ask me if you have any doubts. Whether they make a tricolor right? Then XYZ color space. You just read and understand what are the differences in between these three designs, right? So, and try to do these examples. If you have any doubts, then we can have another session before exams. So I suppose these are very easy. You have to use your calculator and do these things, right? So this is about the color spaces and colors. So last week we have discussed colors and how to nomenclature it, how to write down the color values. And today we have discussed color spaces and how to calculate the color differences, right? So I'm going to wind up the session. If you have more questions, you can ask. So if not, we can wind up the session, and please try to do these examples. And if you have any doubts, please contact me, or then we can do another session with the errors and the things you have to understand. Today also we around 7 people. So I think you all can do as a group, and let me know if you have any questions. So thank you very much for your participation.